so good afternoon, everyone. Real pleasure for me to be here. So, very big thanks to the organizers for the invitation. It's such a nice place, and also in this broad topic, at least mixing people coming from different communities. So this is very interesting. So what I'm going to talk about is a recent experiment. Sorry?
I can't hear you.
You can't hear you, so I don't know. Shall I shout louder?
Is the microphone on?
It is on, and I'm totally wired. All right. So this is recent work that appeared in this paper recently, so where we observe a non-equilibrium super-radiant phase transition. So far there is nothing really new. The thing which is new is that in free space. Okay, and I hopefully will try to explain you why this is so. So before I dive into the topic, so this is our group at the Institut Optique. So the Institut Optique is 20 kilometers south of Paris, and it's not strictly speaking in Paris. And for everything that I'm going to present you, this is the work of Antoine, a PhD student, Giovanni with the postdoc, Sarah, another PhD student, and Igor Ferrier-Barbu, who is a permanent staff member in our group. And just as a short advertisement, but everyone has the same slide, I know. We're looking for people. So in our group, we have 3 experiments where we deal with cold atoms that we try to manipulate by light in different ways. So we have an experiment where we create arrays of individual atoms. So each spot here corresponds to one atom, and we make them interact by promoting them to Rydberg state. We have another experiment where we take a dense atomic cloud, shine light on it, optical light if you wish, and we look at what happens. And finally, we got a third experiment that's in construction that kind of merges the 2 techniques that we learned from there. So essentially trying to arrange atoms in space and explore the physics or the quantum optics of this system of interacting dipoles which are induced by light. And so very recently we were able to have like elementary arrays of dysprosium atoms, which actually is a good candidate to implement a lot of the proposals that we've heard about from Darek. All right, so what I'm going to talk about is this project. Okay, so take a random ensemble of atoms. The typical interparticle distance is a fraction of the wavelength. Shine light and see what happens. So it started a while ago for us, like a very simple question. If you take a dense cloud of atoms, so you shine light, what is going on, and many things can go on. So either you scatter light in free space, or you can also have the spin excitations that hop from one atom to another in exactly the same spirit as what Darek told us. So this is a very well-explored topic, and so people have in mind many possible applications. So I just flash a few of them, only with my own bias coming from the field of AMO physics. So you can build atom-like interface, we just heard that. You can make photons interact. You can also try to engineer the spacing of the atoms to build more accurate clocks. You can investigate topology as well, and you can also look at this under the eye of driven dissipative many-body system, and this is exactly what I'm going to do for what I'm going to present. Okay, so we know what is the general framework to understand light scattering from a collection of emitters. So we just assume first that the emitters are 2-level systems. And then the space that you need to work in to describe the system is these 2 to the n states, which we can build in this kind of Dicke ladder. So essentially we can have all the atoms in the ground state, all in the excited state, and you've got many states in between sorted by the number of excitations. And so we're going to simplify the thing to the extreme, exactly along the way that was proposed by Dicke. We're going to assume that the sample is smaller than lambda to start with, and we will ignore the coherent part of the dipole-dipole interactions that Darek talked about. And so if you do that, all this is equivalent to an n-spin system. So actually you've got a total spin n over 2, and you can sort out between minus n over 2 and plus n over 2 and define these collective spin operators here, which defines the ensemble of atoms. So now if you drive the system, actually, you can write this kind of master equation that governs this collective spin. You've got a term which corresponds to the drive by the laser, so climbing this ladder, and another term which corresponds to the dissipation, which is to say the spontaneous emission. So here, you have to be very careful. The gamma that I put in this, which describes dissipation, is actually a single particle gamma. So the whole many-body physics, if you wish, is encoded in the fact that I'm using a spin of length n. The same thing for the classical drive, and this is a laser. And the thing which, in a sense, makes it quantum is the fact that the coupling from one step of the ladder to another one actually scales with the number of atoms in a way which is more or less complicated. All right, so here we have in competitions two things. We have in competition the drive, and we have in competition the collective decay coming from the second term. And this allows you, and that was predicted a long time ago in the late 70s, early 80s, to the existence of a non-equilibrium phase transition. And so in order to do that, I will just try to give you an intuition of why this is the case. People define a collective parameter, which is the ratio of the classical drive, so the Rabi frequency of the light, divided by the collective decay by the ensemble, which is n times the single atom decay. So let's start first by the case where beta is smaller than 1. In this particular case, essentially you can restrict everything to the two lower states of this system, so it's an equivalent of a two-level system, but the two states are collective states, right? I mean, the ground state is all the atoms ground, and the first excited state is one excitation, which is shared among all the others, exactly the spin waves that Derek talked us about, but now, as everything is within a lambda, you don't have the k vector. All right, and so if you look a bit in detail, what you find out is that, of course, there is a collective dipole here. This is the square root of n enhancement, always. So essentially, we've got a competition between the drive omega square root of n, this n, and n gamma, which is the collective decay. And you can calculate for that the collective, the average collective dipole, and these average collective dipoles turn out to be simply the ratio of omega over gamma. So then the n drops out in this case. And second, you can calculate also what is the super radiant rate, or the photon emission rate, if you wish, which is nothing but the average value of the S plus S minus operator. And once again, this thing is independent with the number of atoms and scale at the square of omega divided by gamma. So this, because there is a collective dipole, in a sense looks like a magnetized phase, the magnetization being given by the average value of the spin length, which is this S minus term. The second other extreme case is the case where now the beta is much larger than 1. So essentially, I drive the system very closely, very strongly. And so essentially, when you do that, all the steps here, all the stage of the ladder now have equal population. And what you have is super radiant, which dominates exactly this kind of collective enhancement that we heard many times. So be careful here, the system is driven. It's not like I place all the atoms in the excited state and let them decay. I drive the system at the same time. So, of course, if you are in a regime where super radiance dominates, which is to say spontaneous emission dominates, the average dipole reaches 0, I mean, as for a two-level system. And on the other hand, this collective average value of S plus S minus is now n squared times larger. This is the n squared of the super radiance. Okay, and so essentially, you've got those two phases, the magnetic phase and the super radiant phase, when beta goes from much less than 1 to a much larger than 1. And so it turns out that it is a phase transition, and it's a bit of a debate depending on the approximation that you do, whether it's second order or first order. But essentially, if you plot the magnetization, so the sigma z, or the total SZ as a function of beta, at the thermodynamic limit, you should have this kind of step function. And now when you grow the number of atoms, essentially, you have this kind of behavior with a single atom, that's the usual saturation of the single atom level, to something that becomes sharper and sharper as we increase the number of atoms. And so this is kind of a special type of phase transition, actually, because it's not associated to a breaking of symmetry, but still you do have an order parameter. So it's different from the Landau paradigm or from the topological type of phase transition. But that was pointed out actually kind of recently. So, of course, there are many realizations of that. You have to be careful. It's not usually the exact implementation of the model I showed you. There is a cavity around. We've heard that this morning. So you need to keep track of the quantized field of the cavity. Here, this is a classical drive that I'm using. But there are some regimes where cavity QED can be mapped onto this driven decay model that I showed you. So the system we are using here is a cloud. It's an elongated cloud of laser-cooled atoms. So they are laser-cooled so that the temperature is sufficiently low that you can ignore a Doppler shift, and the position of the atoms is essentially frozen during the time scale we're going to do the experiment. Those elongated clouds, they are created in an optical trap, so it's not represented here, and it doesn't really matter. But at the end of the day, the cloud looks like a pencil shape, which is about 50 wavelengths in length and 1 wavelength in the transverse direction, the wavelength between being the wavelength of an optical transition, as I will show you in a minute. Importantly, the sample is reasonably dilute. It's not super dilute, but reasonably, so that we can, again, neglect the coherent part of the dipole-dipole interaction mentioned by Derek. So in this system, we can either collect the light along the long axis of the cloud or transversally, as I will show you in a minute. So it's very important that you want to map to the driven decay model that you are as close as possible to the two-level structure. So the way we do it, and we operate with rubidium atoms. So rubidium has plenty of a complicated and rich internal structure. But by applying a magnetic field which is strong enough, it turns out that you can reduce all the structure to these two stretch states here, and then it becomes an effective two-level system. So indeed, it does implement the paradigm of an ensemble of two-level system in this way. So the kind of typical wavelength we use, so 780 nanometers, so this is the lambda which is here, and the line width of the transition is 6 megahertz, typical of what we have for atoms. All right, so there is an obvious drawback here. The first thing I showed you with the driven decay model is that it applies to sub-lambda system, and of course the system is not sub-lambda. All right, so but it turns out that despite this problem, we can still, to a certain extent, map it onto this driven decay model, because we need to look at what is cooperative in this case. So to which mode are you coupled to? So assume, and I will use a very classical argument, that you've written a kind of spin wave along the long axis here. And then you ask yourself, okay, let me just calculate the scattering of the light by this ensemble. Then you have the average of the S plus S minus, and you've got this phase factor here in a direction K. And this is calculating the diffraction pattern of a cloud. So essentially, this is something like the structure factor of the cloud. So you see here that now, if I calculate the ratio of the power emitted by these n atoms in the forward mode with respect to n times the power scattered in 4 pi square radiant, I have something which is n times the solid angle of the diffraction cone from the cloud. Okay? So because of that, you see that it's equivalent to having an effective atom number now, which is n times the cooperativity parameter, if you wish, which is how many atoms contribute collectively to the coupling to the modes. So for us, the decay limit would be essentially delta over 4 pi, which is 1. So you would recover, of course, that all the atoms contribute. But the more elongated you take the cloud, the less atoms contribute to this. The thing which is interesting in our case is that despite the fact this solid angle is very small, because the sample is very peaked, yet the total number of atoms you can put in the cloud makes it possible to achieve an effective atom number, which is on the order of 10. And therefore to be able to explore this kind of phase transition that I showed you before. So it looks very much like cavity QED, if you wish, but without the cavity, in a sense that you've got this cloud, which is coupled to a single mode of the cavity. So then you've got the ratio of the power scattering in the cavity mode divided by n times the power scattered in 4 pi square radiant, which is directly g squared over kappa gamma, and you've got the n enhancement that we've heard about this morning. It can also be, but here we don't have a cavity, right? So the cooperative mode is just the diffraction mode of the ensemble. It can also be what people have in waveguide cavity QED, and Darek reminded us about this gamma 1D over gamma. This is exactly the mu that I'm discussing about here, which is the ratio delta omega over 4 pi. Okay. So, as I said, we have two ways to measure the cloud, and this is going to be important to characterize what's going on here. So we can shine the light along the long axis, as it is here. We put some kind of beam block to remove the light that goes forward, but still the cloud scatters light along the axis, and we can collect that onto an avalanche photodiode, a single photon counter. And the same way, we can measure the light transversely using another photodiode. And the two are not sensitive to the same quantity. If I just write the light, once again, which is scattered in a direction k, so this is the average value of these terms, so essentially sigma plus sigma minus, when you take all the cross product, plus the term I've actually just showed you before, which is these correlators times this phase factor. It turns out that if you look transversely, this phase factor averages out to 0. The reason for this being because there is some average positioning of the atoms, and therefore all these phases go to 0 in average. So along the transverse direction, we directly access what is called the magnetization, or to say the excited state population in the cloud. So this is essentially measuring the average value of total SZ of the cloud. On the contrary, for the other part here, we are mainly sensitive to the S plus S minus, which is to say the light emitted, the intensity of the light emitted in the superradiant mode. So we are sensitive to the correlations between the spins in the system. All right, so let's do the experiment. So we start with measuring the light transversely here. So essentially, we just drive the system. So we apply some short pulse of light, 150 nanoseconds, while the atoms are in free flight, so we've dropped we switch off the dipole trap. And we operate in a regime where we drive quite strongly the system, and this is what we observe as a function of the signal. So this is essentially a Rabi oscillation that you observe on a single, on an optical transition. So it does oscillate, and you have here two lines, the fit to the data and also the prediction of the Bloch equation for an independent, isolated two-level system. So you see that essentially, at low atom number, what you measure transversally is exactly what you would have for a single individual atoms. So nothing collective going on there. And so when you increase the number of atoms, so this line, the dark one, is still the guide to the eye, and the solution for independent atoms. And you do see that we see some kind of suppression of the oscillations in the system. Okay, so indeed, increasing the number of atoms kind of suppresses the oscillatory behavior of the cloud, which is not totally what I would have expected. I would have expected some kind of omega square root of n enhancement, and that's not at all what we observe. Quite the contrary, actually, because if now you try to fit the data by a sign and you kind of plot an effective Rabi frequency, so that's just the oscillation frequency of this sign, you do find that as the number of atoms increases, the Rabi frequency decreases, actually. We've plotted that as a function of the effective atom number, this n times delta omega over 4 pi, and this is the solution of the driven decay model with no free parameter. This is just, we measure everything independently, so that's just the theory put on the data. And as you can see, it kind of works very well. So now we can also plot the very same quantity at a given atom number as a function of the drive, the intensity of the drive. And we observe that at very low frequency, essentially we have no oscillation frequency. And when we drive very strongly the system, we recover at some point the independent particle behavior. And this is very reminiscent of what people had calculated. So this is this prediction from Dan Walsh and collaborators in the 80s, where they plot exactly the same quantity as a function of the beta. So there's a factor 2 missing, but it doesn't matter. And you do observe that there is exactly this kind of phase transition at beta equal 1. So this is what actually triggered us to look a bit more in detail in the existence of this phase transition. So now, why is there this suppression of the Rabi frequency? Well, it turns out that you have a screening by the surrounding dipoles. So if you just assume now that you've written some kind of spin wave in the cloud with the driving field. So this spin wave is going to be of the form, so e to the I k or k naught dot Rn, and I will put here an amplitude which is independent of n. So essentially, I'm assuming that the only things that varies with space is this phase factor. So this is an approximation, obviously, but it's a good starting point. And then you can write the Ehrenfest equations of motion for the individual spin in this collection of atoms. So you just assume that you work in the mean field, so therefore you can factorize the correlators, and you find out that the spin of one atom in there is going to be essentially driven by the sigma z, as it would be for an independent atom. But here you've got an extra term on top of the Rabi drive. You've got this term, which is again sigma minus times n times nu times gamma. So what is that? It's just the fact that if you single out one atom in there, it's going to see the average field created by all the others, which turns out is going to screen completely the influence of the field. So essentially, there is no light into the system there. And at low drive, because if beta is smaller than 1, I showed you and I've given you the solution of the Rabi, this driven decay model, and we've seen that the collective spin was minus I omega over gamma. This is exactly what is needed in order to cancel this field inside the cloud. Yep.
So what's how do you explain that I in there, or what's the significance?
Say that again?
There is an I in there, so there's some kind of a phase.
This is the usual I that you have for a single atom. I mean, it's if you are driving on resonance, there is a pi over 2 phase shift in the dipole. That's just this I. That's all right? Or? Yeah. Okay. So essentially, you've got these two regimes. So the regime at low drive, where you've got a screening which is perfect, and of course, when you try to overcome when you drive strong enough, then sigma minus increases up to its largest value. So this term has a maximal value, so which corresponds to all the spin polarized, and the largest value being 1/2. And therefore, omega then overcomes if you go beyond this point, where essentially that corresponds to beta larger than 1. All right, we can also observe what happens in steady state now. So we wait until the regime has kind of reached steady state, and we experimentally define the steady state, and when the signal, the oscillation does not vary any longer. And we can plot the average value of essentially NE, so this is just the value of this plateau, but just shifted by between -1 and 1 to define some kind of magnetization. This is what we have for small number of atoms as a function of beta. And when we crank up the number of atoms, which is to say, we crank up the number of atoms, this is what we have on the data. And once again, those are the solution of the driven decay model. And I remind you, this is what people had calculated a while ago. So essentially, this is the same phenomenology that we observe here than the one of the driven decay model for a point-like system that was predicted a long time ago. Okay, so you can also look at it in more recent eyes, and many people with more, fresh eyes, so to speak. So people have calculated a lot the mean field diagram of this kind of ensemble of atoms. So those were worked by Igor Lezanovsky, but there are many other people who looked at this, and essentially they all calculate something that looks like this, and it's always in the mean field that those things are done. All right, you can also calculate the the super-radiant emission, which is to say the light emission along the axis, as a function again of beta, and we do observe that at low atom number we have this very small emission, and when we crank up, we have this kind of emission that increases. And importantly, if you kind of look at the scaling of this emission at strong and low drive, they are very different as a function of the number of atoms. So you do observe that if you drive the system strongly, you have something in n to the square, which is exactly what you expect for the super-radiant phase. There is a debate with the student of Darek, but we have to sort that out. But essentially, naively, the super-radiant says that it should be n squared. And what we observe is that at low drive, it scales linearly with n. Okay, and so this is just kind of the same plot where we have all the power law as a function of omega. Now you see there is kind of a phase transition, and once again, from between 2 and below 1. And once again, the solution of the driven decay model. So the model seems to apply very well in free space, and despite the fact that the cloud is not sub-lambda. All right, so there is some kind of connection between this and what people are trying to do in mini groups and trying to observe super radiant lasers. So people have observed the very same quantity as a function of the number of atoms as well. And in the super radiant phase, they do observe that the power radiated along the axis of the cavity, which is exactly what we measure here along the long axis without the cavity, should scale like the square of the principal quantum number. And there are several works, either with thermal beam or cold atoms, that have showed that. All right, so the last thing I wanted to show you is to try to do a bit more quantum optics. Let's try to analyze the statistics of the light which is emitted along the long axis of the cloud. So essentially the question we're asking is the following. If you observe superradiance in the cloud, it means that you've got atomic correlations, because you do need these sigma n, sigma m correlators to be present, otherwise there is no superradiance. That's the term which gives you the n square. So if you have atomic correlation, can we say that the statistics of the light has to do with those atomic correlations? So in a sense, you are asking the question, what is the connection between the statistics of the light which is emitted and the correlations between the spins or the two-level system inside the cloud? So in order to do that, the answer in quantum optics is just put a beam splitter and measure in a Hanbury-Brown and Twist type of setup the correlations first at equal time. So what we do here, we drive the system, we place those two detectors here, and we measure the intensity correlation at tau equals 0 in steady state. And so this is the probability to get a click on one photodiode when you just got a click on the other one. And you observe that as a function of beta, the G2 of 0 that we obtain, the number of correlation, varies from nearly 1 to this value of 1.4. How can we explain that? I mean, if you are in the regime where beta is smaller than 1, I showed you that this is essentially a classical dipole which is driven by light. But if you were asking in your classical electromagnetic textbook what is the G2, you would find 1, exactly the G2 of a laser, if you wish, because this is just a classical field. And this is more or less what we observe here. It turns out that the question of what is the relation between this and the correlations inside the system is actually more complicated and more interesting than it seems, because it turns out that the spins inside the cloud would be correlated in a way that it generates a squeeze state. And so this is something that people have on Shamoon in the Weizmann Institute has demonstrated recently. So it means that there is no trivial relation between the G2 of the light and the statistics of the correlations between the atoms. And so the other thing, we have partial bunching. So just as a teaser, what we've done is that instead of looking at tau equals 0, we look at tau non-equal to 0. And we observe that if we have a small number of atoms, then the G2 of tau shows something which is consistent with a bunch of independent emitters. This is called the Ziegert relation that you may remember from your classical textbook. So this is something that we measure. But on the other hand, if you crank up the number of atoms, you do violate the Ziegert relation. But more interestingly, you do see the appearance of oscillations now, not only at the frequency of the drive, but at twice the frequency of the drive. So which is signing the fact that this driven decay model is actually non-linear, and the non-linearity comes precisely from this internal field of this screening, which goes like the dipole itself. And as a consequence, it gives some kind of non-linear term in the Ehrenfest equations of motion. So we're kind of surprised to observe that in the lab, but it turns out that people had calculated that a long time ago, again, Agarwal. And so we gave even an expression for this, and this is what you see here. All right, so the model is predictive, so that's nice. So even this pencil-shaped cloud, which is not sub-lambda, has all the phenomenology of the driven decay model, even at the correlation function of the light level. The only thing you need to do as a recipe is to change it to an effective atom number. We've observed this non-equilibrium phase transition, and to our knowledge, this is the first time that steady-state superradiant has been observed in free space. Usually it's done with a cavity. Here you don't have that. And it turns out that maybe there is some kind of link, and I'm not quite sure how deep this is and what I can make of this information, but people are talking about the driven decay model realizing a time crystal, boundary time crystal. So this is something that I'm throwing at you because I still don't quite understand what we learn from this information. And so there are a few buts that we are looking at. So why does it work, despite the fact that the cloud is not long? So this is something we are looking at with Darek, and also how to connect that to the cavity model exactly, and whether we have some link with the chiral waveguide model that was presented this morning. And with that, thank you very much for your attention.